Welcome back to the Grid Beyond Energy Trends podcast. We're really excited today to be talking with Akaysha Energy, both Eric Wallace and Riley Sample, about data centers and the strains and opportunities that they're putting on the grid at large, and how battery storage can help unlock a lot of potential for data centers as well as the wider electric system. So really salient topic today. Really excited to have Eric Wallace here, General Manager of Development Engineering, Riley Sample, and Energy Market Analyst, both from Akaysha Energy. Thanks so much for being on, guys.
Great to be here, Alden. Thank you.
Thanks for having us.
And I'll note a few things before you tell us more about Akaysha, but Akaysha is a market-leading BESS builder, owner, and operator with a very large portfolio in Australia. 2 gigawatts, I think, in the books, and 710 megawatts operational as of late 2025. So congrats on that. I know it's a big push at the end of the year here. Are there any projects in particular you want to highlight from your Australian experience?
Yeah, so we'll highlight our flagship Waratah Super Battery. It's currently got 350 megawatts in operation, but once complete, will be the most powerful battery in the world, at least for a short time. We'll see what happens in the market, but slated to be 850 megawatts and 1,680 megawatt hours at full COD.
Very cool. Well, I'm excited to see it briefly, at least, be the most powerful battery in the world. And as you said, everything's growing so quickly in this space that we'll see what the future holds in terms of being overtaken by larger assets. One of those large assets that we're spending a lot of time thinking about right now at Grid Beyond are data centers. So Grid Beyond, we work front of the meter as well as behind the meter. So we sort of see a really interesting intersection of the data center space, and increasingly are doing these sort of around the meter solutions where you may have assets that function as sort of part one configuration, part one of another. We'll get into sort of behind the meter, front of the meter, around the meter, and all of that later on. But I'm curious how you guys are thinking about data centers right now. What is the approach been at Akaysha for how you adapt to the opportunity of the data center space?
Yeah, so I think first and foremost, Acacia is a very mission-driven organization focused on enabling the global energy transition overall. And then it's really great to be able to add on to that layer, kind of the new paradigm in the US for significant increasing load, and more specifically around large loads and data centers. So I think as an engineer, it's really exciting to have a complex problem presented to us, especially if we can approach it and find solutions that are aligned with our broader mission, right? So I think part of it is just an exciting technical challenge, and as well as like a huge opportunity to build more systems and really big batteries to enable this growth.
Definitely. And Eric, you mentioned briefly, sort of the engineering challenge here. I know that you're working a lot on development engineering. It would be great to hear from you, Eric, and then you, Riley, on sort of what your roles are focused on at Akaysha, and how you got into the space.
Sure, I'll lead us off, Riley. Like you mentioned, I'm the GM of development engineering here at Acacia. What that generally means is I oversee a small team of engineers focused on supporting our development teams with siting reviews, early concept design, system sizing, single line drawings, and then transitioning into supporting our commercial teams with initial scoping and pricing with our preferred suppliers, kind of modeling out who we might select for a project, what the different products are on the market and which are preferred for a specific use case, and supporting those commercial teams through contracting and technical schedules, all that negotiation, all the way up until financial close of the project. So really, the bulk of engineering responsibilities, with the exception of grid studies and interconnection work ahead of contract.
And then my role as an energy market analyst is what it sounds like, analyzing the energy markets across the US and Canada, really all of North America, focused on market modeling, supporting our commercial and finance teams through revenue analysis, load projection forecasts, picking and choosing which markets we want to play in, helping with offtake contracts, and really getting into the nitty gritty of what does it mean when something says it in an offtake contract. How do we actually functionally do this and ensure that we're protected against any risks or downsides or upsides.
Awesome. It's great to hear about sort of the little niches that people find themselves developing that expertise in. And one thing that I've really appreciated in having these conversations with other folks in the battery industry, especially, is sort of how did you get into batteries? It's such a new industry.
Hmm.
Eric Riley, where were you in batteries from? Sort of the inception of your career? Did you come to batteries from renewables or another segment of the power industry?
Pretty broad base for me. I like happy they use the word niche. I like to refer to myself as a niche generalist. I've been in various roles kind of throughout renewable energy or green energy in general. I've worked in solar PV system design, residential and commercial scale. I've worked in energy efficiency consulting, design consulting, and testing and validation on new construction buildings. After that, was interested in the next phase, and about 5 years ago, transitioned into battery storage at utility scale, and have just grown from there.
And then for me, I graduated in 2022, so fairly recent to the space, but started out in natural gas modeling and consulting, and then moved to really renewables, and then batteries from there.
Very interesting. Yeah. Well, I appreciate you sharing sort of more on your background, both you and Akaysha, and I think that's really good context for sort of talking about the main, focus of this segment, which is data centers and then the challenges and opportunities they present on the grid. So, sure, many listeners will be familiar with this, but we are seeing unprecedented load growth and load growth projections. A lot of that driven by the build out of domestic data centers in the U.S., complemented maybe by the sort of reshoring of manufacturing. But we're expecting over 100 gigawatts of load growth by 2030 across the U.S., which is just a huge scale. The hyperscalers, the AWS, Microsoft, Googles of the world are driving massive investment in the space. Some of the economic reporting coming out of the Federal Reserve from this fall was showing that without the data center capex built out, the U.S. economy may be in a recession. So this is just a huge driver of the economic stage that we see ourselves in, as well as maybe the national security stage that I think this industry is getting a lot of focus for right now. And really, as part of that, power is a huge expense for data centers. Always has been. We've seen this on the Grid Beyond side with things like the moratorium on data centers in the Dublin area in Ireland, where Grid Beyond is based. Really pushing out any sort of interconnection for data centers several years into the future. I think we're starting to see those sort of similar timelines come to some of the U.S. markets with time to power and time to get that data center online being a real competitive advantage as utilities and grid operators alike are pushing out the available interconnection dates for these very large loads. And when we say large loads, I mean, these can be 100 megawatt, 500 megawatt. I think there's some talk of gigawatt scale data center campuses. So, just a huge amount of power, the size of cities coming online at single facilities to do a lot of the cloud infrastructure, AI compute training, as well as other opportunities like Bitcoin and other cryptocurrency mining that Gridbound has worked with for a while. So a lot of different diverse players in the data center space, a lot of money going into the space right now to solve the challenges that this presents. And one of those main ones is that time to power challenge. So one recent transaction, I mean, I think this is last week as we're talking about this, sort of in the interstitial week between Christmas and New Year's here in the US. But the there was a major transaction with Google's parent company, Alphabet, acquiring Intersect Power, who's a solar plus storage developer with about 10 gigawatts in their pipeline coming online before 2030. And the total price of that acquisition that was announced last week was $4.75 billion. So maybe not the largest power or largest renewables transaction ever, but certainly up there. And I think a real bellwether of where the competitive advantage lies for data center developers looking to acquire megawatts that are going to hit the ground before the end of this decade. I've talked a lot there just to sort of set up the framing here. I guess I'm curious from you guys, how are you thinking about data centers, maybe what they mean as, unique customers maybe, and then what are the concerns that you're hearing from utilities and grid operators that are trying to bring online these large loads?
Riley, I might kick it to you to talk about scale of the problem.
Yeah, so I mean, when we look at a market like ERCOT, if you look through their TSP provided interconnection queues as of early December, it's 223 gigawatts in the queue. Just large loads looking to connect before 2030. That's just ERCOT. And if you look at historic peak load in ERCOT, that's around 87 gigs. So really a 2.5x of historic peak just in ERCOT alone. And so when we look at this, especially from a load modeling perspective and a network build out perspective, it's really difficult to say how much of this is real, what's actually going to be built, how do you plan the grid of the future, and how do you ensure that you actually make the right investments in the system to ensure you're not just building stranded assets, spending billions of dollars on massive transmission lines to nowhere. I think that's the biggest problem that utilities are having today, and ensuring that they're not just modeling phantom load that will never come on when they're building their IRPs and ISPs.
I think then I would add on from like our perspective on a technical design standpoint, what is unique about a data center, both a legacy type of data center as well as a more modern AI data center. What are the problems that they're running into for connecting to the network, and then how do we solve that as a battery developer? So I think a lot of it fits into a few clean buckets. One being just load itself, kind of just the bulk quantity of load, and grid operators doing their modeling, telling a data center developer that we have certain constraints, we need network upgrades, it's going to extend your connection time out to here. A battery being placed with a data center to allow additional flexibility to maybe cover specific periods of congestion on the network and shorten that time to power. The other would be, instead of just the bulk amount of power, the actual load profile itself and unique characteristics of operation of a data center, whether that's around ramping profiles, if it's AI load jitter during training periods. Batteries are uniquely positioned to solve a lot of those with their like really millisecond response times, can handle a lot of that. Um, and then I think the additional buckets would be things like reducing demand charges, kind of cost savings on behind the meter side.
And Eric, you mentioned there, the point around sort of traditional data centers versus AI training data centers. And the other piece that I'll mention that we work a lot with at Grid Beyond are cryptocurrency mining data centers. And I mention this just because the load profiles of those systems are very different. And so I came from a demand response background. We've talked about, can you do demand response with data centers for years, right? And the traditional data center it was always a hard no, right? If you are processing payments, you have absolutely no flexibility in any sort of downtime for your data center. But as you mentioned, maybe a behind the meter battery or behind the meter generator could go on site to back up that load, help participation in the electric grid flexibility events, often via demand response programs, right? So you've got maybe a traditional cloud infrastructure data center over on one side where there's no flexibility of the latent load, but there could be flexibility of the assets on site. And then maybe on the other end, Grid Beyond works with hundreds of megawatts of cryptocurrency mining data centers in ERCOT that can interrupt at a second's notice, right? We'll do a dynamic co-optimization of the price of Bitcoin against the price of energy, right? And can very quickly take these data centers offline for load flexibility events. And I think there's a lot of thinking right now around that sort of new emerging class in the data center space around AI training and what is the flexibility profile of AI training data centers. So there's some really seminal work being done by Tyler Norris, who is at Duke University, just went to Google himself to look at, sort of how much flex can you actually get out of those AI training data centers, and what sort of type do they most look like, right? The 24/7 no interruptibility type or the highly interruptible type. And I think the thinking right now is that they're somewhere in the middle. So a study that Duke put out found that you could bring online 100 gigawatts of new load with only modest flexibility of the underlying assets, less than 1% annual curtailment, and each of those events lasting less than 3 hours. So from sort of a solutions perspective, batteries to me sound like a great top line example of how those potentially inflexible data centers could support flexibility in their operations to participate in grid events, to be good grid citizens, and hopefully, I think for them to get those assets online faster. So I think that's a really interesting space of where does the battery go in that configuration. And obviously with Akaysha's expertise, I think that's what we'll talk about next. That, that sort of bucket of like, where does the value lie, probably has a few different, ways to think about it. The highest one that we talk a lot about is like reducing time to power. There's also managing the load volatility itself and sort of the power quality issues that come up with that. Grid Beyond focuses ourselves a lot on reducing the operational costs of, operating a microgrid that could also be used in grid programs. And then I think there's maybe a large but shrinking emphasis maybe on improving resiliency and sustainability. And I think that's a really interesting piece that we can talk about. But those are sort of the four buckets that we see: speed to power, reducing operating costs, managing the load volatility and the power quality, and then enhancing the resiliency and sustainability of the system. Would love to dig through those with you guys if you want to maybe start with talking about time to power as sort of a huge value driver in this space.
Yeah, I'm glad you brought up the Tyler Norris study. I think a lot in that study refers to this flexibility as curtailment, and how do you achieve quote unquote curtailment with an asset that really can't afford to be curtailed at all. Like, it has to be 100% available, working 24/7. You introduce methods of being flexible, and yeah, the amount of time duration that a lot of these events that are needed to add this flexibility seems tailor-made for a 2 or 4 hour LFP battery to slot into. Time to power, I think, is the main bucket that we're hearing from the market when we have talked to certain developers or utilities. There's value to be added, like you said, with reducing operational costs and man charges. But the time to power is the big one, and that can be either shrinking the amount of time that a network upgrade takes, or the amount of network upgrades that are needed. Maybe that battery is servicing as kind of a bridge asset so that the system is able to connect and operate with added flexibility for 5 or 7 years while all those network upgrades are happening in parallel. It can also be just a binary thing, like the utility is scared of data centers, protection and relay settings, and the potential for load rejection. So the network has straying frequency or voltage values, and the concern could be that the data center it's drifted far enough that it's in danger of its operational parameters, and it just shuts off completely from the grid. That can have cascading effects where, okay, now it has more impacts on the frequency on the grid, and now that data center down the street is going to low reject, and then the next one is going to turn off, and you've just caused a cascading event through your whole distribution network or transmission network. So batteries being able to fill gaps like that, where utilities are concerned about the actual behavior of the site and may just say, no, we will not connect a data center that operates that way. You can go from a no to a yes. So it's not just about managing network upgrades and these kind of long lead times of different things, but also going in that binary.
Definitely. And go for it, Riley.
And one concern that we've definitely heard, especially with the battery, is not doubling load at that substation. Instead of 100 megawatt request, now you have 200 because battery does need to charge at some point. But really, this can be solved pretty simply by telling the utility, hey, just restrict our charging periods through the solar hours or overnight when load is lower. And that just gives that even greater sort of, I don't know what you call it, but certainty that you're not doubling that load. That flips that no to a yes, like Eric was saying.
Definitely. And I'll just plug quickly, Grid Beyond's doing studies on exactly this, sort of like what charging and discharging restrictions are needed for specific, substations generally, but other sort of parts of the grid to ensure that a battery can be brought online safely. And so to the extent that anyone listening wants to talk about sort of how do you think about charging restrictions, what impact does that have on total project profitability? This is something that we're modeling for utilities and for developer partners right now on how much restriction does this how much impact does this restriction being placed on the asset have? And I guess the spoiler alert is generally not much. You're usually making your money during infrequent but really important periods of discharge, and so the actual charging restriction can be less impactful than folks think. And so I think that, and realistically, batteries are great at managing that sort of load volatility. And Eric, I'm glad you sort of, started to talk about the cascading effects, the other, sort of load rejection potential implications that this can have on distribution systems. Is there anything else on sort of how you're thinking about what the balance of that battery providing critical backup power or on-site power quality versus providing sort of grid support services are?
Critical backup power is probably not as big of a primary use case here. I mean, just the natural limitations on battery duration, and how long a site may need to be disconnected from grid and have really firm, like consistent, long duration backup power. Um, I know that in some examples as well, like that may not actually be that big of a concern for some developers of data centers, where instead of having a bunch of, backup generation on site, they just build a duplicate data center somewhere else that is connected to a different part of the power network, different data connection, different climate and kind of natural disaster characteristics for the location, and so you just have a duplicate system, and that gives you that availability by just having like literally a fail safe. So probably not as big of a solution there, but can slot into filling, the really short duration or quick response time gaps there. So if you do have some sort of on-site generation, but has, a 30-minute hour ramp up to get the full capacity, batteries can be an excellent bridge in that situation where you need to disconnect from the grid fast. You can't afford any downtime. Your availability requirements are 100% for your facility. Batteries can fill that ramping gap pretty easily for your on-site generation.
Definitely. And we've seen that use case and serving as that bridge be really salient. The other piece that I think is helpful there is that if you're not relying on the battery for primary backup of the facility, you actually have more flexibility to participate in energy market demand response or ancillary service events with the full
Hmm.
capacity of that battery. And so you don't have to try to figure out what the right state of charge, co-optimization is between a resilience use case and a energy market use case, say.
Hmm.
The other piece I think that the use case we've seen for batteries with data centers and maybe other industrials coming along is using those batteries for sort of timed hourly generally matching of renewable load or renewable generation with the load. And Google again has been a sort of pioneer in this 24/7 carbon free space, but just thinking about batteries as potentially a hedge for your energy market position or as a hedge for your emissions profile that you're looking to hourly match, I think is a really interesting use case. And then I guess maybe one more that we have talked around is that like reduction of operating costs or sort of energy market revenue piece, right? So Grid Beyond works behind the meter batteries, front of the meter batteries. One of the good things about putting a battery behind the meter is that you can peak shave, right? If you're in ERCOT, you can do 4 CP peak shaving. If you're in PJM, you can do 5 CP peak shaving. If you're in Ontario, you can do global adjustment. There's a variety of ways to sort of save on your electric bill with more flexibility that batteries can introduce. And then on the other side of the savings are the revenue you can generate from the energy market. So, we see that batteries are a great asset to be able to participate in some of these programs. And a lot of those programs are available to behind the meter customers just as much as they are to front of the meter customers. So I think as folks are starting to think about when does that bridge to power become less of a critical bridge and you're maybe running your gas recip engines less than 24/7, or your batteries are no longer being used for sort of a primary resiliency use case, there's a reduction in operating costs that folks like Grid Beyond bring to the table for being able to use those flexible assets either behind the meter or front of the meter in the energy market. So I think that's a few years out realistically from sort of top of mind for data center developers because there's so much of an emphasis right now on building that bridge. But eventually that bridge could be amortized more cost effectively, which is probably less sexy than building the bridge up front. But I definitely think that's an emerging space that we're excited to see is what other uses do these microgrids have as that bridge to the main utility interconnection comes in.
Yeah, it's a good point, and it's like I think demand charge reduction, peak shaving things. It's not a necessarily new use case. I think it's pretty well understood. Um, tariffs and things like that on your retail arrangement with the utility are always pretty well defined, and it's easy to calculate how you're going to save money there. Like you said, it's maybe not as sexy because it's not as new. And the key important thing is that we're hearing over and over again is time to power and just getting connected in the first place. And yeah, good point. And Riley can talk about this more, I think, than I can. But if you are able to connect front of meter instead of doing, your kind of standard demand charge reduction, hedge against those variations in power costs by operating in the merchant market if you're building in an ISO or RTO.
Yeah, I mean, just having that opportunity to open yourself up to the energy markets and be able to trade the asset, especially for sophisticated traders, it really just reduces your costs so much further and allows you to possibly even make money on that side if you do everything correctly, which is a tough thing to say after the year we've had in ERCOT.
Yeah, certainly challenges on the energy market side. I mean, you mentioned ERCOT, KISO sort of similarly have seen reduced revenues from where they were a few years ago. Um, for data centers specifically, and thinking about those batteries and where they go, I think there's also challenges with like behind the meter interconnection and the engineering complexity that introduces. So, Eric, I guess I'm curious from your engineering expertise, is this something that you talked about with customers in terms of what complexities does that introduce to projects, and what's your thinking, I guess, both personally and as Akaysha on where do these batteries best fit in that value chain?
Yeah, so I'd say, we're talking about two systems, the data center facility and the battery facility that have pretty complicated controls and networking architectures. Going behind the meter, trying to operate everything as a single asset is just going to raise that complexity even further, right? Um, and I like in terms of our preference, I think we would much prefer to be front of the meter. And I think it opens up more opportunities for what we can stack in terms of use cases. If we're looking further down the line, like you said, like, hey, once we're past this time to power constraint scenario, maybe in the after 5 or 7 years of operating as with an offtake contract specifically to cover that use case, what is the next opportunity for that specific site? Being front of the meter, you're going to have a lot more flexibility, especially if you're in a deregulated market.
So, Eric, you mentioned the control system on these assets, and controls are something that, to be honest, spent a lot of time thinking about. We started as an industrial controls company in the early 2000s, realized we could sort of use industrial controls for energy market revenues with demand response, and then came to battery storage a few years ago as they become, really a dominant asset class in the flexibility space. So having that sort of controls paradigm top of mind when you're thinking about the system, I think is really valuable. So there's not a gotcha moment down the road where you maybe, got uh, got investors excited about the expectation that this would be able to play sort of both sides of that behind the meter and front of the meter use case without realizing the engineering complexity that is going to introduce. So maybe not to dissuade listeners from at least evaluating that, because there are great benefits to that configuration from a accessibility of savings perspective, and potentially from a time to power perspective if the utility agrees that this could be a really viable asset to bring your data center online faster. But just to flag that the controls will be much more complex. The financing as well will be much more complex. These are often financed sort of as two infrastructure projects side by side without the sort of linkage in the middle. So there's engineering and financial engineering complexity that you introduce with that. But if you are, sort of interested in pursuing those sort of controls arrangements, or really a microgrid level sort of data center energy supply strategy, would be happy to talk with folks about that offline on sort of what we could participate in on the control side to orchestrate that around the meter flexibility, as well as helping with sort of the modeling of the financing between those two, but deeply interconnected asset classes. So a lot of really interesting, I think, engineering work to come in this space, but certainly a very large barrier to a rinse and repeat model that I think a lot of developers are, reasonably trying to get to keep costs down. So it's a part of the space that we're watching very closely is how do you orchestrate all of this flexibility between the front of the meter and the behind the meter solutions.
And a lot of that design complexity is only as good as your modeling, and you're going to get into real life scenarios where you can do as much testing and kind of pre-integration work that you think you can do, and then you're going to get on site and you're going to learn how these control devices are actually going to integrate and operate together, and how it matches your grid modeling, your performance modeling, and everything else.
Definitely. And I think a lot of folks are thinking a lot right now about that modeling, right? Like, where does the data center boom sort of go next? And Riley, I'm curious from your perspective, looking at the energy markets around the country, we see this evolving in different directions in different regions, right? I mean, ERCOT versus PJM, say. And I'm curious as to your thoughts. What do you see coming down the pipe for the major markets that you're operating in terms of structures to support data centers or to support flexible interconnection more generally?
Yeah, I mean, it's really market dependent, right? If you're in the regulated WEC, it's pretty straightforward. Bilateral contracts, nothing fancy, fully tolled, with some delivery and wheeling charges if needed. In the ISOs, ERCOT, I mean, you're going to start to see a lot more complex offtake agreements, moving away from your basic standard fully tolled asset, or revenue floor plus share, into more of what we are seeing in the NEM, in Australia, with virtual tolls and capacity swaps, where with a virtual toll, you see basically it's a virtual battery that you're nominating every day. And the asset owner trades against that. Capacity swaps, similar thing. It's basically the same thing as a revenue floor plus share, except the owner is trading the asset instead of the off taker. Um, I think in PJM, I really don't know where PJM is going today. I'll be honest. PJM has a lot of complexity right now, especially around the capacity markets and ensuring that there's reliable load. I mean, they cleared at the market cap twice in the past year and a half, however long it's been, and now are starting to see deficiencies. They still have a pretty healthy reserve margin, but you're starting to see the capacity crunch. So in a market like that, I imagine you're going to see a lot more behind the meter, directly connected, similar to what the non-capacity backed load proposal was before it got rejected by all stakeholders. In SPP, you're seeing Hills, which is the most fascinating program that I've ever seen, although that's not saying that much. 90-day study turnarounds, until you get your interconnection agreement. Really fast, really quick moving, but that requires either same POI or local area, and local area being within 2-3 buses. So you're not seeing an asset, say ERCOT West, going to Houston and dealing with that kind of financial toll. You're seeing got to be right near each other to ensure that the system is working. So I think with everything we're saying, you're going to start seeing a lot more standardization across the markets, taking best practices, what works, what doesn't, and really start to go towards the middle and figure it out. But it is going to be an interesting couple of years seeing what that end goal actually is.
Definitely. And you brought up the Hills program and SPP. I agree. It's a fascinating program because it is really leaning into that sort of around the meter flexibility space that we're seeing evolve quickly, as well as, in other markets, like we're doing this with municipal utilities in places like PJM and ERCOT. But having an asset that is located not behind the meter, but around the meter at the same substation is a lot of the work we're doing, or as you mentioned, sort of within the local distribution grid topology, alleviates a lot of the challenges that data center coming online would bring to the grid, but doesn't necessarily introduce the same level of complexity that putting a 100 megawatt battery behind the meter does. So I think that sort of, around the meter space, same substation or very close by, is something to watch, and maybe a best practice that other deregulated markets start to take up as well.
Yeah, and Alden, I'll just add there. It really comes back to who the customer for the battery is. Is it the data center or the utility? Um, who cares more? And my guess is it's the data center who's trying to get online, and they are at the behest of the utility in ensuring that they can get that connection. Although the utility may see some standalone assets out where load may be going in and try to contract with them to provide services for the data center around the meter. It really depends on where in the asset lifecycle you are and where you're building. That's my view.
I think
Definitely.
the around the meter concept is a really great one. Like we mentioned that our preference would be to be front of meter. It opens up additional opportunities for us. But if our goal at the end of the day is time to power, and a utility is uncomfortable with adding a, potentially doubling the load at that substation, if they are going to take the conservative approach and say, what if you're charging your battery at full power while the data center is operating at full power, which may not be a very realistic scenario, as you alluded to, Alden, but um, we still at the end of the day need to get utilities comfortable with that, or whatever solution we are proposing. And if a behind the meter solution is what is getting the data center faster time to power, then that may be the path forward. Or if we can come up with alternate solutions like this behind the substation or around the meter, whatever the name is that you want to use, uh, probably opens up a vastly higher amount of opportunities for everyone.
Definitely. I think there's a lot to come in this sort of space of where can highly flexible assets, and generally we're thinking about batteries for a lot of that, unlock greater grid benefits. And so I think it's certainly something to watch for batteries as well as for other technologies, whether those are new generation nuclear reactors that could provide baseload power to data centers, or highly flexible gas or other liquid fuel engines we're seeing, like in the linear generation space, or even sort of more standard HVO or gas recip engines. I think there's a lot of different technologies that will have a part to play in supporting the immense load growth that we're starting to see. So we're talking about the differences between those asset types and new asset types that may come online to support these data centers. I mean, cost is a key consideration here, as well as sort of the operational characteristics of those different assets. Eric, I'm curious, how are you thinking about like what asset is right for the job in terms of operational characteristics of BESS versus other assets? And then what are the cost implications of using different technologies to support data centers, or in offtake agreements generally?
Yeah, absolutely. So we hinted a bit earlier about BESS maybe not being right for your longer duration off grid power support, but where it does shine is use cases where you need fast response times, or in use cases where you need fast deployment. So like servicing that time to power requirement that all these data center developers are facing. So battery, from a financial close to COD for most of our just standalone grid battery assets, we're talking 1.5 to 2 years. There's a lot of work that goes into development ahead of that, but that's a really fast turnaround time. We're talking about lead times from suppliers around 9 months, well under a year, versus natural gas turbines that may be able to supply some of these use cases where we're talking about lead times well north of 5 years in some examples. On the cost aspect, because of those supply constraints on natural gas turbines, to pick on them again, the, the capital cost for them has gone way up, and then obviously necessarily their offtake agreement costs have skyrocketed in parallel with that. NextEra just put out a report showing their kind of baseline battery offtake cost estimates versus their natural gas offtake cost estimates, and that's really in line with both the capex numbers that we're seeing for our projects, as well as research we've done on capex for natural gas turbine systems. So their baselines were $8 to $12 per kilowatt month for a battery. That's fairly in line with our estimates in terms of 2-hour or 4-hour systems, and then double that for a natural gas supplying the same thing. So batteries will really slot in well in both delivering the power that you need faster, as well as addressing specific use cases that require really fast response times.
And Eric, just to add there, that number you quoted for a gas turbine also doesn't include any sort of natural gas infrastructure that's needed to tap into the line, the storage potentially, any sort of firm contract for gas if you're not just buying spot. So it really is a fairly major cost difference.
Well, Riley, great point on the sort of natural gas build out and sort of how to study these loads together. Eric, as you mentioned, a lot of the sort of various technologies have different implications sort of in terms of what flexibility they can support on the grid. And I think that sort of cost operational profiles are two of the major considerations that folks need to be thinking out for in the months and years to come around the build out of energy supply for this space. I think the other piece that it's worth watching really closely is around the regulations and how those are evolving. So I know one piece that we're looking at really closely is the FERC and NOPR process, which we expect to conclude somewhere in sort of Q1, Q2 of 2026. Riley, I know this is something you've looked at as well. So what's going on with the FERC and NOPR and what should listeners look out for in the first half of next year?
Yeah, no, this is really FERC's response to making sure we standardize this process and have some sort of best practice across the U.S. electric grid. And I will note that this has no implication in ERCOT. ERCOT is not a FERC jurisdiction, so it's important to keep that in mind. But really, the big things that come to mind for me are hybrid studies, ensuring that if you have a large data center and a large generating facility at the same substation, these are no longer going to be two different study processes. This will be one, which really alleviates a lot of network upgrades, issues that may come up in these studies, and it really works. Another big thing is if you have a curtailable load, you will be expedited. So opening yourself up to that flexibility and being able to be flexible, that's a good thing for you. So it's really the federal government trying to ensure that we connect all of these data centers in a timely fashion that makes sense for the grid, that doesn't harm the grid at all. So having that all work together is really important. And this is something that we focus on a lot at Akaysha, especially with any sort of large load customers that we may have, is how do we get you connected as fast as possible and as reliable a fashion as possible.
Awesome. Well, I really appreciate the conversation today, guys. I mean, I think we hit on a really great breadth of topics, from the flexibility of the grid that could be achieved with sort of, minimum additional flexibility, say, to serve the enormous load build out that we're looking at. Obviously, time to power coming up in all the conversations that you all are having, that we're having as well, and the benefit that provides to those large load customers looking to come online quickly. And I really appreciate the discussions of sort of behind the meter versus front of the meter viability. Something we're thinking a lot about at Grid Beyond, having sort of feet on both sides of that equation, and how do we support that around the meter space that's evolving here. And then definitely keeping a close eye on that regulatory momentum. Batteries can be a hugely complementary resource. A lot of this depends on what the utilities, the grid operators, and the regulators will require of large load customers and the developers supporting them. So, Eric, Riley, thanks so much for sharing your insights today. I'm sure folks found it a really insightful conversation.
Yeah, great conversation. Appreciate it. And probably just add another plug that we've got a pretty sizable pipeline in Australia. The pipeline here in the U.S. is kind of just getting off the ground, and we view this space as like a really key part of that pipeline. So encourage any listeners to reach out to us directly to talk more about how we can build batteries to solve your problems.
Awesome. Thanks, guys. Appreciate the time.
Thanks a lot, Alden.
Thanks, Alden.